Hey everybody, welcome back to another round of physics, and yeah, let's get going here. Um, yeah, today's topic we are going to continue on. We've taken care of Kirchhoff's laws, and now we need to keep moving. And one of the first things that we should do is talk about what happens when we have a circuit that combines multiple circuit elements. So the idea being, what do we do for an RC circuit? Circuit. So let's go ahead and think about the behavior of RC circuits. And first of all, I'm actually going to start with a discharging capacitor just because that makes the differential equations easier. And then we'll work our way into the charging capacitor circuit. And then we'll see where we go from there. So imagine for a moment that I have a fully charged capacitor. So I'll take a fully charged capacitor and I will go ahead and I will connect it to a resistor. Okay. And the pieces of information that we know, let's assume that we know the initial potential drop across the capacitor, having fully charged it. We know the resistor value, and we know the value of the capacitor. Put C in here. Okay. And the question is, what is the current flowing through the circuit? What is current I flowing through the circuit? Now, the caveat is that I is no longer a constant. It's not constant. And the reason for that is because as you remove a charge from the capacitor plate and let it run around the circuit and combine with the other side, the additional, how would I say it? The strength of the electric field between the plates decreases, and so the current will slowly decrease, right? If you're not, for lack of a better word, pushing the charge as strongly, after you move the charge around, the next one gets a little easier to move, et cetera, et cetera. You're not pushing it as hard, and so you would expect that the current is not going to be constant anymore. This is where a charged capacitor will differ from a battery, right? A battery is designed to maintain a constant potential throughout the entire lifetime of the battery. A capacitor does not. So let's see if we can come up with the expression that tells us what the current is flowing through this circuit. Well, let's go ahead and let's follow our rules. We said number one, we should label I's. We should put the I's in. You say, well, that's, I want to say, it's pretty straightforward here. We only have one branch. Okay, so we only have one branch. And for, I'll just call this I. We only have one branch, so we only have one I, and I'm just going to choose it to be going clockwise because I seem to choose clockwise all the time. So we're done there. Now that we've given our I, we should probably label our high and low sides. So if I do it this way, this side is the high side on my resistor, this side is the low side. And you're probably, okay, well, we'd probably say, well, how do we know which side is high and low on the capacitor? Here we have to remember that the capacitor is the object responsible for providing the difference in the electric potential. The capacitor is the energy source right now. And so current is going to flow from the top plate of the capacitor around the circuit to arrive at the bottom plate. So I'll label those high and low. So we've got that. Number two, highs and lows. High, lows. Number three, sometimes you can swap these around, but number of unknowns. Well, again, in this case, the number of unknowns is 1. It's not by accident. I chose this simple circuit to kind of get us a feel for how to actually get the equation. So it's 1. And so number 4, we're down here. Go ahead, apply KVL and KCL. Well, of course, KCL isn't going to be helpful, not in this situation. So KVL it is. And so I will choose the upper left-hand corner, and I'm just going to walk around my loop. So we'll put it down here. So what do we have? We have our jumps must be equal to our drops. So we'll walk around the circuit and we hit the resistor R, and that's a drop. So taking advantage of Ohm's law, we'll put in here IR. And we keep walking and we hit the capacitor and we find out that it is a jump. Okay. Now be careful. I've already warned you. I cannot put V naught in here. Right? V naught would not be the right thing to do. And that's because that is the initial drop across the capacitor, the starting drop, or excuse me, I said drop, the starting jump across the capacitor. But as time goes on, that jump across the capacitor slowly decreases. So we can't put V naught in here. V naught is a constant. We have to come up with more of a generic expression. So here's what I should ask you. Pause the video, come up with it. What's the general expression for a potential drop across the capacitor? You got it? Good. So the potential across the capacitor, way back when, we defined capacitance as being the charge on the capacitor divided by the potential difference between the two capacitor plates. So we're going to plug this in, and we can put Q, the charge on the capacitor. In fact, I'll put QC here, remind us this is the charge on the capacitor divided by C, excuse me. For a minute there, I almost wrote V. There we go. So what I want to highlight here is that the fact that there is a capacitor in this circuit, we still treat it the same way. We go through, label highs and lows, let's put Kirchhoff's laws in, and we still get an equation. Don't forget, Kirchhoff's laws describe energy, they describe charge. It doesn't matter if there's a battery or a resistor or a capacitor in there. Okay? You can still do the same thing. Now we'll have to take a little byline here for a moment. Okay, so let's go ahead and do this. Okay. Now I want to think about this charge on the capacitor for a moment, the QC. And I'm going to think of it as being some initial value, which I'll call Q naught. And then as I hook up this resistor, I start drawing charge off of the capacitor plates. And I'm going to think about if I draw the smallest charges possible off that plate, one at a time. Oop, there goes one, there goes another, there goes another. You could say that the charge on the capacitor is the initial charge, the starting charge, and you probably see where I'm going here. I'm going to remove some little tiny charge. I guess I'll call it dq. Is that okay so far? Good. So here's the next question for you. So I've put this in here. And please bear in mind, this is, actually I should put this is the starting charge. Starting charge. And this is the charge that's been removed. In other words, this is the charge that has flowed through the circuit. Removed charge. Okay. Now here's the next question for you. How does my current I, the current flowing through the resistor, relate to the charge that has been removed from the capacitor plate? Hopefully you see. Right? What is I in the first place? I, my current, is how much charge has passed in a given time. So if dq represents the charge removed from my capacitor, dq dt must be the current flowing through my resistor. So I'm going to go ahead, let's go ahead and do it this way. Let's go ahead and take this equation right here, and I'm going to take a time derivative and sub it into right here. So I have I is equal to the charge on the capacitor. Oops, excuse me. Let's do it this way. I have I is equal to the initial charge, the starting charge on the capacitor, minus the current charge on the capacitor. And then, of course, that's what dq is. I'm taking a time derivative of that. And then, yes, what can you tell me about Q naught? Constant or not constant? It's constant. So the time derivative of a constant is 0. So I can write this as the current flowing through the resistor is negative the time derivative of the charge on the capacitor plate. Okay. Now we're home free. What we needed to do in order to solve Kirchhoff's equation is that we needed to somehow relate the charge on the capacitor to the current flowing through the resistor. And so now, well, let's take our current and we're going to plug it into our equation that we had using Kirchhoff's laws. So let's go ahead and do that. And incidentally, just for reference, I'll call this equation 1. I'll call this one equation 2. And I'll call this one 3. So what we want to do is take 3 and sub it into 1. So we're taking equation 3 and we're subbing into equation 1. So let's write down equation 1. From Kirchhoff's law, we had this. And now we can say QC over C equals negative R dq C dt. Go. You have an equation. Solve it. Alrighty. I'm just going to point out a couple of things to you. Okay. One of the things that we should notice is that this equation is what we would call separable. We can get the QC's on one side and we can get the times on the other. So let's go ahead and work our magic here. We move the dt to one side, the q's to the other, and I can write something like dt over RC, I'll keep the negative sign in there, equals dQC over QC. Okay. Now I'm out of space at the bottom, so I'll come back up here to the top. And what I now need to do is I need to integrate. So I get something like, I'll put 1 over RC. Don't forget, those are constants, right? The resistor and the capacitor. But I have some time, I'll say from 0 to t, equals dQC over QC. Now at time equals 0, the charge on the capacitor is Q naught. And then at times, some time interval later, we don't know what that's called. I'll just give it Q. Just call it Q. And we go ahead, we integrate. Well, this is a piece of cake. That's just t. And so we get something that says negative t over RC equals, what should I put here? Good. ln. This is the ln of, we'll put Q minus the ln of the initial starting charge, Q naught. Of course, I want to get Q by itself. I want an expression. We'll start off with an expression of Q as a function of time. Once we have the expression of Q as a function of time, we can get the current. So we're after this value for Q. Let's go ahead, and I'm going to take advantage of one of the properties of logarithms. When you have the difference of two logarithms, you can express that as a fraction. So we'll go ahead and let's take care of that. We have negative t over RC equals ln of Q over Q naught. Remember, logarithms, one way to think about it is that logarithms will take division and turn it into subtraction. Now, how do we get rid of a logarithm? We raise the logarithm to whatever the base is. Now, this is a fancy logarithm. This is the natural log, so this is base e. So we need to raise both sides of this equation to the eth power. So we take e negative t over RC. And on the right-hand side here, we just, the raising the power of the natural log, that just undoes everything. Those are reciprocal operators. And so I can just write Q over Q naught. And since I want Q by itself, I'll go ahead, let's write this. This is Q. The charge on the capacitor plate is given by the initial charge on the capacitor plate times e to the negative t over RC. Pretty cool, right? Of course, but wait, there's more, right? What happens if I want the current running through the circuit? Okay. So I can call this equation 4. If I want the current running through the circuit, equation 3 tells me how to do that. I take the charge on my capacitor and I take a negative time derivative. So let's go ahead and do that. So let's say this is the charge on the capacitor as a function of time. Let's find the current running through the circuit as a function of time. Well, I need to take a negative time derivative, Q naught. So I need to take a time derivative of e to the negative t over RC. So I'll let you go ahead and do that for a second. Good? Awesome. So we have our current as a function of time is equal to, well, the negative and the negative cancel out, so I end up with a positive again. I get Q naught. The time derivative of the exponential is just the exponential again. And of course I have to chain rule it, so I end up with an RC out here. Boom! We've got it. Of course, if you really wanted to, Q naught over C, that was the initial potential difference across the capacitor plate. So we could even go further. We could write this as I equals the initial potential difference divided by the resistor in the circuit, e to the negative t over RC. And there we are finally done. We have an expression for the current running through the circuit as a function of time. Let me ask you some questions here. I mean, number one, it would be something like, well, at time equals 0, what's the current running through the circuit? Well, it's just V over R, which looks a whole lot like Ohm's law, right? At time equals 0, this exponential disappears. E to the 0 is 1. And so we have something that looks like V over R is equal to I, Ohm's law. Just for that brief instant when current starts flowing, it looks kind of like Ohm's law. But then after some long time, you notice this is an exponential decay, the negative sign in the exponential. At some long time, say time is really, really long, the current running through the circuit is 0. Again, that's what we would expect. If the current is due to moving charge from one capacitor plate to the other, we are slowly discharging the capacitor. We are slowly taking that electric energy, the energy that's stored in the electric field, and turning it into movement of charge through the circuit. When we actually deplete all of the electric field, there's no longer a charge separation on the capacitor plates. There's no more energy stored in the electric field. We'd expect the current to go to 0. Pretty cool, huh? Okay. So there's one bit. Okay. And of course, once you have the charge on the capacitor, if you'd prefer, you could get the potential drop across the capacitor. It's still going to be an exponential decay. Cool. Well, let's go for another round here. Let's go for something a little bit more interesting now. And so we will start off with this. Let's now say that we have a situation where we have a fully discharged capacitor. So it's not charged at all. And we're going to go ahead and there we go. So say we have a capacitor C, a resistor R, and a battery potential. Just call it VBAT. Okay. Capacitor is fully discharged. Okay. Go ahead, write down, apply Kirchhoff's laws, write down an equation for me. Hopefully pause the video. I'm going to go ahead and say again that my current is flowing clockwise. Now this time, since I'm dealing with a discharge capacitor, nothing's actually stored. That would mean that now this is the high side. This is the low side. We have high and low. The capacitor is not responsible for driving that current. That's the battery's job on this circuit. So I've got my highs and lows. So if I go ahead and start writing down my equation now, and I'll write it like this. I'll say the drop across the capacitor plus the drop across the resistor must be equal to the jump across the battery. And of course, we have an expression for the capacitor. I'll put this as Q over C. We have an expression now, we have an expression for the drop across the resistor. That's just Ohm's law. So we'll go ahead and put Ohm's law in. And this is just the V battery, some constant here. Now let's ask ourselves, let's ask ourselves the situation now. How does the charge on the capacitor, maybe we'll call this QC for a moment. How does the charge stored on the capacitor compare to the current I that crosses through the resistor? Here they are related, directly related, right? If there's charge that gets put onto the capacitor plate, if I put some charge onto the upper capacitor plate, that forces some charge off of the bottom capacitor plate, and that charge must pass through the resistor. So in this situation, the current is actually the time derivative of the capacitor charge. Okay. Whatever charge flows onto the capacitor plate, that also must flow through the resistor. Yeah, so now I have some relationship between my charge on the capacitor and the current. Okay. I'm going to do one more thing right here. Okay. We have a couple different ways of going at it. Okay. The way that I'm going to go at this equation is I'm going to take a derivative of both sides. So in other words, what am I going to do? I'm going to get dqc dt, and I have a 1 over c in front, plus, and I have an r, I'll say di dt equals, now here's the reason I did this, it just makes it easier to figure stuff out. Look at this. The battery is a constant. And when I take a time derivative of a constant, I get 0. Go. Solve this equation for the current running through the loop. Hopefully, good. You got it? Okay, well, let's keep in mind we have an expression for dqc dt. That's just the current, I. So I'm going to rewrite this more suggestively as 1 over c times I plus r di dt equals 0. And again, we have a separable equation. You should be able to get the i's on one side, the t's on the other. And it looks almost like the equation we had for our last example. It's just that instead of Q, the charge on the capacitor plate now, what we have is I, the current running through the circuit. So let's go ahead and solve this. And you're probably already way ahead of me. So we have something like, oh, okay, well, I'll move 1 to the other side. So I have 1 over RC I equals negative di dt. And let's get the i's on one side and the t's on the other. So I have a negative dt over RC equals di over I. Sweet. We better think about our integration limits for a moment. We better think about our integration limits for a moment. There's a couple different ways that we can do this. I'll say let's start with 0 to t for the time. And on the right-hand side for the current, go ahead, think about what would the limits of integration be for the right-hand side. Let me ask you this. At time equals 0, how much charge is on the capacitor plate? None. 0, right? Okay. So for that brief instant when we start charging the capacitor plate, there is no drop across the capacitor, which means that this initial current at the very beginning, when you close it, I'll call it VI naught, right at the beginning, it's just the potential of the battery divided by the resistance of the circuit. So I'll just put this down as I naught right here. And then I'll just put I here, I final. Well, let's do our song and dance. We'll come up here to the next side. And what we have is something that says T over RC equals the ln of I divided by I naught. And we work our magic, right? Raise everything, take the natural number and raise everything to the natural number to that power. And we end up with something that says, hey, I naught times e to the negative t over RC equals I. And we'll go ahead. We'll plug this in right here. V battery, since those are the things that we actually know, over R e to the negative t over RC. Well, that's interesting. What does this say? At time equals 0, it's almost like the capacitor doesn't exist for a brief instant. At time equals 0, the charge on the capacitor is 0. Therefore, the change in potential across the capacitor is 0. Just for that brief time. How about time equals infinity? What can you tell me about the current when time is equal to infinity? The current is 0, right? I is equal to 0. Well, what does that tell you about the potential drop across the resistor? If there's no current, that means the potential drop across the resistor must be 0. Oh, incidentally, if the potential drop across the resistor is 0, that means that the potential drop across the capacitor must be equal to, yeah, very good, the potential drop across the battery. Yeah, nice. Very good, very good. Okay, well, let's go ahead. Now that we have an equation giving us the current through the circuit, let's go ahead and find what the charge on the capacitor is. Let's find the charge as a function of time on the capacitor. Well, we have that I is equal to the time derivative of the capacitor charge. So let's go ahead. What we need to do now, again, this is a separable equation. We can get the t's on one side, the q's on the other, and go at it. So let's go ahead and do that. We have V bat over R, that's a constant. And then I have the integral of e to the negative t over RC dt. And on the right-hand side, we just have the integral of the charge on the capacitor. Let's think about our limits of integration again. At time equals 0, how much charge is on the capacitor? 0. Remember we said that we started off with an uncharged capacitor. And then the upper limit will just set some time interval t and some final charge q. Go ahead, solve this equation. What's the integral of e to the negative t over RC? You got it? Well, I'll go ahead. I'll say V bat over R. Excuse me. And because we're doing the integral, okay, we need to have this RC and then e to the negative t over RC. Oops, excuse me, I forgot a negative sign. Put that negative sign in there. You can double check. If I take the derivative of this, do I end up with that? Well, e to the negative t, well, okay, that's, repeat that, okay. And then the chain rule, I have a negative 1 over RC, that'll cancel this out in front. Yes, that worked, oh, right, good, good, good. And don't forget, we need to evaluate at 0 to t. And right here we have QC evaluated at 0 and Q. Now be careful. Okay? Tendency is to say, oh, it's evaluated at 0. The answer is 0. Okay, so be careful there. Look at this. We have an R canceling an R. Let's go ahead and get rid of that while we're at it. That's always nice when we, oh, goody, goody, get some sort of cancellation right there and there. Okay. So we write it out. We have V battery times our capacitance times e to the negative t over RC. And this is negative. Don't forget we have a negative sign right there. And then we have minus a negative V battery times C times e to the 0, which is 1. So this is just 1. So we have 1. That is equal to, just say Q. And let's go ahead. We'll get rid of the negative signs. We'll pull out the common term. What do I have at the end of the day? I have V battery times C, 1 minus e to the negative t over RC. Let's see if this jives with what we expect. At times equals 0, this is 0. E to the 0 is 1. Excuse me. Yes, now I did it. At time equals 0, we have e to the 0, which is 1, and 1 minus 1 is 0. So there's no charge on the capacitor. After a long time, right, as time goes to infinity, e to the negative t over RC goes to 0. Remember, there's the negative sign in the exponential, so it dies out. Okay. So at long time intervals, this goes to 0. And I get that my final charge on the capacitor is equal to the potential of the battery times the capacitance. That jives. That's the kind of thing for the capacitors, the definition of the capacitors. So now we have two things. We have the current going through the resistor as a function of time, exponential decay, and the charge on our capacitor as a function of time. And you can't say that this is exponential growth. No. Exponential growth is something like e to a positive exponent, e to the x. This is not exponential growth. What is this? Well, I will hand draw it, and then we'll plot it in some better program here. Say as a function of time, and you have Q. What is this? This is, I'll do something like this, where this is the asymptotic behavior. It'll get close but never touch. And this value will be V battery times C. Okay. So it'll just grow and get really, really close. And eventually it'll just, that's the limiting behavior. Okay. So to recap, okay, for a discharging capacitor, and then I'll have a charging capacitor. Okay. Well, let's see. The current in the circuit is given by something like e to the negative t over RC. In fact, we can go back here. V naught over R. Of course, I should have known that. Excuse me, I shouldn't have had. So the initial charge on the capacitor divided by R. Okay. There we go. For a charging capacitor, it looks the exact same, except instead of the charge on the capacitor, it's the battery charge, or the battery potential. So instead of the potential difference across the capacitor, it's the battery instead. But otherwise, these two things look the same. But now if we're talking about, this is the current running through the resistor. If we're talking about the charge on the capacitor, so for the charging capacitor, this would be something like V battery times your capacitance and 1 minus e to the negative t over RC. So for the discharging capacitor, we had something like Q naught. Okay. So that would be the initial charge, the initial potential difference on the capacitor times C. And we had this e to the negative t over RC. Okay. Cool. And that's everything. Of course, if you want to know the potential drop across the resistor as a function of time, then you just use the current as a function of time and multiply by R. Or if you want the potential drop across the capacitor as a function of time, just take the charge as a function of time and divide by the capacitance. So once you know I and QC, you know your potential drops. The last point, the last thing I'll mention here, you notice that this e to the negative t over RC, that popped up all over the place. That happens enough that we give RC its own, I don't want to say definition, but we give it its own term. Okay, RC comes up so often, we give it its own term. This is sometimes referred to as the time constant of the circuit. And often we'll give it its own variable label as well. We call it tau. So we define tau, the time constant of the circuit, as being defined as RC. You might say, why is that? Okay, why do we call it a time constant? And from a unit standpoint, okay, are you allowed to have a unit in the exponential? No. What does it mean to raise, I don't know, 1 to a second? You know, say you take a number 2. Let's say 2 raised to the 1 second. Well, what does that actually mean? Units don't belong in exponentials. So what that means is that if I have time in the exponent, okay, and time has units of seconds, then RC must also have units of seconds. Okay? So RC must also have units of seconds. We could try to hack that out. In fact, maybe that's a good exercise. RC is an ohm, and C, capacitance are in farads. Okay. Well, let's see. Let's see. What's an ohm? An ohm, if I think about Ohm's law, V equals IR. So an ohm must be a volt per amp. Okay. And if I think about the definition of capacitance, that's a Q over V. Okay, well, so capacitance, a farad, must be charge divided by potential. Oh, goody, goody. The potentials cancel out. The V's cancel out. And I better think, what's an ampere? Oh yeah, let's see. An ampere is a coulomb per second. And of course I have times a coulomb. Oh, well, that means the coulombs are going to cancel out. And I have 1 over 1 over seconds, which is indeed a second. So it turns out that when I take a resistance times a capacitance, I end up with units of seconds. That's why we call RC a time constant. And sometimes, rather than seeing it expressed as negative t over RC, you will sometimes see it expressed as e to the negative t over tau. And furthermore, you will sometimes see one time constant elapsed. Time constant elapsed. What this means is that t is equal to tau, and therefore you have e to the negative 1. This corresponds to roughly 0.36. So for example, if you have a discharging capacitor, after one time constant, the final current, the current after one time constant, will be roughly 0.36 of the initial current. V naught over R. Or if it's two time constants, say Ti is, you evaluate after two time constants. Two time constants, I think, is 0.5. I don't know. What's e raised to the negative 2? Let's try that again. Parentheses are important. Oh, no. Okay. So this would be something like 13%. I'll round to 14. 14%. Or three time constants. After three time constants, this would be something like e to the negative 3. And you get something, okay, well, last one, e to the negative 3. This one is about 5%, so you get 0.005. Just to give you an idea. So sometimes you'll see it expressed as time constants. You'll express time in terms of tau. And that just gives you some easy references. Good so far? I think that's good enough. We'll call it quits there. Say, go back if there's any questions you might have, write them down, review them, bring them to class, and we'll have something to discuss for tomorrow. So, hey, thanks for your attention. I'll see you next time.